Hello, my name is Nikita. I'm the author of Laminar, a UI library for Scala.js. This video is a broad and comprehensive introduction to Laminar, suitable for both Scala developers as well as JavaScript developers interested in type-safe UI development. I will start off by explaining the structure of Laminar application and showing you a few component patterns and reusability techniques for Laminar. I will also discuss the core ideas and principles behind Laminar and contrast Laminar's approach with the Virtual DOM approach of React. I will also talk about some issues with observables, as well as how Laminar's design overcomes those issues. Finally, I will show you how to easily integrate Laminar with React and how to use web components from Laminar. The video description for convenience contains a table of contents for this video, as well as a list of all the links that we use in this video. Now, let's go learn something new. So, what do you even need a UI library for? Well, the surface presented to the user by a UI application is the UI state. So on the web, that would be the DOM, the tree of elements that the user can look at and interact with. Then internally, we have application state, which is like a collection of Scala objects which tell us what should the UI state be. And the role of the UI library is to, first and foremost, keep the UI state in sync with application state. And that goes both ways. So if you update your application state, say you change what name you want to be displayed somewhere in the UI, our UI library needs to efficiently update the DOM to make this happen. And on the other hand, if the user types or clicks or scrolls something in the UI, we should be able to respond to that, including by updating the application state, which in turn might update the DOM. So we'll have this like interaction loop going on. Now, you can do this totally in plain JavaScript with no libraries or with some super low-level library like jQuery. However, when building complex, rich, and interactive applications, this approach is not very scalable, to more than one developer or to more than one weekend, because it's too imperative. The logic is just too granular and it's hard to maintain. And so we have UI libraries that provide, as they say, a declarative way of expressing your UI logic, which is a higher level and makes it easier to work with. React, for example, achieves this with Virtual DOM and callbacks. Outwatch, another Scala.js UI library, achieves the same with Virtual DOM and observables and typed effects. And Laminar just has observables, and well, we don't need anything else, and that I do like this, to be honest. I'll explain why. Laminar uses observables because they are first-class representations of state and events, which are exactly the domain of UI libraries, as we just saw, so that's very fitting. Observables are also universal, which means that they don't depend on the DOM and are not aware of the DOM even. And so you can use observables to express the entire data flow of your application, even the parts that don't touch the DOM. So it's very nice to have it universal like this, to be able to reuse the logic and think in the same data structures. For the record, Laminar uses my own library called Airstream for observables. It's pretty simple, but it does have a couple interesting solutions to common observable problems. We'll talk about those later. For now, just the standard stuff. We have event streams, which just used to represent events, and we also have signals, which represent state. Now, state is different from events. It is not just a collection of discrete events. State is a value changing over time, and that means that signals always have a current value. They start out with an initial value, and they continue having a current value throughout their lifetime. Both event streams and signals are read-only in the same sense as Excel formulas are read-only. You can't write it directly into them, but they depend on parent observables in one way or another to get their current value or the next event. But we do need to bring values into the observable chart somehow, and for that we have event bus and the var. You can write values manually into those types. For example, you can write an event manually to an event bus, and it exposes an event stream of all the events that you write into it. And then you can use this event stream, you can depend on it, you can build other observables from that event stream. And similarly, var, you start out with an initial value and then just fire events manually into it, fire the new states into it manually, and it exposes a signal of those states that you pass to it. So these are the 4 types of reactive variables that we have available to us in Laminar. So let's see how we use them. Let's get on the same page regarding Laminar's syntax and DOM tree structure. Here we have an application that apparently creates a div element and then an input element with some props and then a span element with a string hello world in it. And well, then it renders it. So this is exactly what's happening. How exactly? For every HTML tag, we have an apply method. So div.apply and then input.apply. And what it does is create the corresponding JavaScript DOM element. So in this case, that would be the underlying JavaScript DOM input element. And then this apply method accepts an argument list of modifiers. And the modifier is like an instruction to do something with that element. So in this case, this is a setter modifier, which sets a certain property to a certain value. So immediately after the input element is created, we apply every modifier that we've passed to it in sequence. So first we set the class name property, and then we set the placeholder property on that input element. And then we return this input element. But as you see, the resulting input element is passed into div.apply. So this input element must also be a modifier itself. And yes, it is. And what this modifier does is create the input element as we just described, and then appends this input element to the parent element, which is the div in this case. Here's a bit of what looks like an inconsistency. Hello world is not a modifier, it is a string, but we have an implicit conversion for convenience defined that converts strings into modifiers that append the string as a text node to the parent element, so to the span in this case. Span, again, being an element, is also a modifier which appends itself to the div, but because the modifiers are executed in sequence, by the time span modifier is executed, input is already in the div, so it appends itself after input, which results in the DOM, which looks exactly the way the code looks. No surprises there. Finally, all of this is considered the root element of our application, but it exists in a detached state. It's not attached to the DOM. To attach it to the DOM, we need to call Laminar's render method. This is something you only do once per application, much like a React DOM.render. You pass it the container element, which is presumed to already exist in the DOM, returned by the server, and also tell it to just render the root element inside of that container. Everything you need in Laminar is imported from this one import. You don't need to hunt for implicits, there are no macros and nothing like that. This is all native Scala, which is very convenient. So this is a complete but inert application. Let's add some observables to it so that we can see some actual behavior happen. I have upgraded our static Hello World application so that when you type your name into the input element, the application actually prints it back to you, character by character, live as you type. To do this, we create a reactive variable, var, to represent the state, the current name that the application should print. And we started off with the initial value of world, which is just so that when the application opens, we're going to print hello world and not hello and then nothing, because that just wouldn't be very friendly. So let's see how we read and write into that name var. We listen to its signal, which, as you remember, contains all of the updates coming in, all the updated names. And then we uppercase it, producing a new signal of uppercase names. We pipe it into child.text, which is Laminar's way of saying, please listen to the observable on the right-hand side and insert the strings that it emits as a text node in this location, replacing any previous text node that this observable has inserted in this location. So it will always say hello and then whatever is typed into the input element. And yes, this is a modifier, and what I've just described is what it does when it's executed, when it's applied to the span. Now, how we write into namebar. You can see namebar is on the pointy side of the arrow here. which means that whatever's on the left is being sent to namevar. And specifically, this describes both what will be put into the namevar and when. On input is the when part. It's a browser event that fires on every key press as the user types something into the input, or it also fires when the user pastes something into this input. And what we're mapping it to is an expression that lets us grab the text value, the current text value of this input element. The unfamiliar thing here is in context, and it's simply a wrapper that provides us with an easy reference to the input element that we've already created. And this node is this reference. This is the input element. So what we're doing is we're getting the Laminar element, calling .ref on it to get the underlying JS DOM element, and then calling .value, which is the JS DOM way of getting the text from an input element. Right? So to recap, whenever the user types something, we grab the text from that input, whatever is typed in there. We send it to namevar, and namevar's signal then emits the same value. We uppercase it, and we print it out after hello. So as you type your name, character by character, it will appear after hello. As you see, working with observables is actually very easy in Laminar. This is a complete application that you can just go and run. As I mentioned before, Laminar does not use virtual DOM, unlike React or AutoWatch. That means we don't have virtual elements, and we don't do any diffing, like DOM reconciliation, child reconciliation, stuff like that. There's none of that in Laminar. Laminar is very direct. When you create a div element, we create that div element. It's not like virtual DOM, where it's like a representation of it that the virtual DOM might choose to instantiate or reuse a previous div node for this div node. Like, there's none of that magic. This is very direct. You call div apply. This is going to create an underlying JavaScript DOM element, and it's going to be immediately available under .rev. And it's going to be the same instance, the same reference to that element for as long as you have this element in scope. This is very convenient because when you need to access the underlying JS DOM element, for example, to measure its dimensions, to focus on it, or to do something else that Laminar doesn't give you a direct API for, like setting all the props, you don't need any boilerplate. You don't need the React refs or anything. You just say .ref, .focus, for example. So you might be wondering, oh, isn't this a performance problem? So let's see how it is not. Rendering lists of children elements efficiently is really hard. This is probably one of the most challenging performance problems for UI libraries. And to clarify what I'm talking about, say you have a list of users, maybe 1,000 of them, and it updates over time with some user names updating or adding new users, removing users, rearranging them. This is the kind of thing that is really hard to render efficiently without a special algorithm. So in React, that would be virtual DOM. In Laminar doesn't have virtual DOM, but we have something else. But first, let's look at how to do this the dumb way in Laminar, the most inefficient and just overall bad way to do it. So whenever you get a new list of users from the event stream, for each of them, we basically create a span element, printing out the user's ID and name. When you fire the first event, you're going to create 1,000 span elements for 1,000 users. And that's fine because every library would do this. You do need those 1,000 span elements because you want to show them in the UI. But say on the second and subsequent events, what this code is going to do is it's going to discard all the previous span elements that we've created and recreate 1,000 new ones every time, assuming you still have 1,000 users in the list. And that is grossly inefficient, of course, because instead of performing a small set of updates, you're just nuking everything and recreating it from scratch. But performance is not the only problem. You're going to lose DOM state in this manner. For example, if the user has selected the user's name in the UI, in one of the elements, this selection is going to be lost when you destroy this element and create an equivalent replacement for it. Or if it was an input element and the user typed something into it, the replacement would not have what the user typed and wouldn't even actually have the focus on it. So it is both performance and functionality that needs to be addressed. In React, the way efficient children rendering works is you need to provide a unique key to every element when you're rendering a list, or in JavaScript an array of elements. And a good candidate for that key would be user ID in this case. It will let React match the next version of the virtual element with the previous version of itself when it's diffing the new list of elements to the previous list of elements. But all this diffing story is a virtual DOM, and we don't have it in Laminar. So how do we live efficiently without it? And the answer is the split operator available in Airstream on Observables. It also accepts a unique key. It requires you to specify a unique key, and we'll use user ID in this case. And you also need to provide a render function that will be called to render a given record, so a given user in this case. However, unlike the previous render function here, this one will only be called once per user ID, once per key, for as long as that key is present in the list of users. So when we first see each user, we create a span element for them right here. But subsequent updates to that user are actually, through the magic of split, channeled into these individual signals for each individual user. And then we can listen to those signals in individual span elements to efficiently update their text with the new name in this case, instead of recreating the span element from scratch. And so if you, for example, emit 1,000 users in this scenario using split, we have not seen any of them previously, so we will create 1,000 new span elements, one for each user ID. But when you send, say, the second event with 1,000 list of users, but maybe one of them has a different name, all that's going to happen is the user stream for just that one user will emit the updated user with the new name and update just one span for that user and nothing else. All the other elements are going to stay completely untouched. And even this element is not going to be recreated from scratch. We're just going to update it in the most efficient manner possible. So that's why split is called split. On a high level, it converts an observable of a list into a list of observables and then provides each of those observables to the corresponding render function. So sort of like sequence in cats, but more opinionated, more specialized. And just to clarify, like say if you emit then 1,001 users to add some new users, we will call span for that one user because we haven't seen it. And then if you remove one of the users, if you emit 999 users, we will remove the element for that user from the DOM, and nothing else is going to happen. And then if you add it back, we're going to again recreate a span element on it. Now we recreate it because, well, we've lost that user. We haven't seen it before. React works in actually exactly the same way. A bit more magic, well, not magic, but like a bit more logic is happening inside of the children receiver. As you can see, it accepts an observable of a list of elements. And so when it receives a new list of elements, it needs to compare that list to the previous list of elements that it saw to determine what operations it needs to do on the DOM. And doesn't that sound like virtual DOM? Eh? But the difference is that virtual DOM performs a deep diffing comparison, whereas Laminar just takes one pass on the new list and it just matches with the previous list of children by reference equality. We're not looking to compare attributes, props, or children, or whatever else React is doing in there. And all we're doing here, and we're not like trying to come up with a set of operations to do on those elements, on the insides of those elements. All we do is just to order them in the right way. So Laminar takes one pass to bring all the elements in the right order. Because say, for example, if you emit the same list of users as before, but it's just rearranged, Laminar is not going to recreate any of the element. It's just going to rearrange them to match the order. And that's the extra logic that's happening inside children. And it's very efficient. Like overall, this is at least as efficient as React transformations would be. We're not doing more work than React is doing. Oftentimes, actually less. So what I like about the split operator is that it's an observable operator. It is general purpose, and it doesn't even know anything about the DOM. You can use it with any other types. And with the power of the observables, that's how we don't need virtual DOM in Laminar. Let's look at a few example components to give you a sense of patterns and techniques that we use in Laminar. This is a counter that renders the current count in bold, as well as decrement and increment buttons to change it. And obviously the count updates live. It works very similar to the Hello World application we just saw, except we have an event bus instead of a var. As you can see, when you click on the buttons, we send either -1 or 1 into the bus, depending on which button is clicked. So divBus.events is basically an event stream of deltas, of changes to the count. And then we fold left over that stream to get a signal that accumulates this value. So if you click plus 2 times, count is going to be 2, and so on. Laminar doesn't have any built-in notion of components, so you are free to organize your code in any way you can think of. Here, counter is just a function that accepts label as input. We use it over here. And it just returns an HTML element, just this one div. And then using it is very straightforward. Now, you could make it more complicated. For example, you might want to expose this count signal to the outside, and you could, for example, return not just an HTML element, but a tuple of this count signal and this HTML element. And then your parent element would be able to access current count and do something about it, like display a warning if it's too much or something like that. Basically, in React, you're used to having props as input, and then your only output is the HTML element. In Laminar, whatever you want is the input, and whatever you want is the output. The entirety of Scala is available to you, so go nuts. Authoring generic components such as TextInput is a unique challenge. On one hand, you want such a component to be flexible, to be reusable from many parts of your application, and by very definition, those will have different requirements. But you can't possibly account for all of those requirements inside the component itself, because it will just become super bloated and impossible to work with or update in any way. So you need some way to extend this component with extra functionality without bloating up the core. And let's see how we approach this in Laminar. So this is a text input component that just renders an input element and maybe an error message inside the div. And well, it accepts the error stream. That's straightforward. But the interesting part, we made this component accept an argument list of modifiers. Mods are modifiers that are applied not even to the div element, but to this node, to this input node. Because, well, that's the important node in this component, right? That's why we made it this way. So let's see how that looks. Here we call this component, we provide the error stream, and then we also provide 4 modifiers. One that sets placeholder, another that pulls a value from the stream, another that listens to on-input events, and finally one that focuses on this input element when it's mounted. This is a completely unrelated functionality, and in some use cases you might want a placeholder or not. You might want the input and the component to be controlled or not in React terms, I mean, and you don't even know which events you care about. Is it on input, on change, on something else, on click even maybe? The author of TextInput didn't have to think about any of that. They just needed to think that this input node is important, so they need to expose a way to extend its behavior. And in Laminar, modifiers is how you extend the behavior of an element. So that's the component part, but here we also have a Laminar way of extending any element. Any element in Laminar, and TextInput does return an element, the div element, has an amend method that accepts an argument list of modifiers, again, that are just going to be applied to it. So it's just a way to apply extra modifiers to an element that already exists. And at the end, it returns the same element, but well, now it has a bunch of side effects applied to it. So let's see what we're applying here as an example. Well, we're applying a different class. Well, that's a bit confusing because this div already has a class name defined in the component. Wouldn't that override it? Speaking of which, wouldn't this stream of class names override either of those? And the answer to that is in Laminar. Laminar is aware that class name is a composite attribute. That is, Laminar expects several values in this attribute. It knows that class name is a list of classes, that it's not just one class. React is happily ignorant of that. You need to use third-party libraries to work with classes effectively, but Laminar has this built in. So the colon equals method, instead of setting a class, it adds a class. And there are methods to set the class and to do many other convenient things about it. And as you get new class names through this stream, this modifier remembers which class names have been set through this stream. And when you emit a new class name, it removes the previous one and adds the new one. So this just works the way you expect. Basically, all you need for this to work flawlessly is to not emit either this or that class name in here. It has to be independent. That would make sense. Background crawler is just a CS property, that we decided to apply. But hey, there's another interesting thing. We've added another child to the text input component that, again, didn't even consider this possibility. So where would the child be added? If you recall correctly, the div or any element, when you apply it, it becomes a modifier which appends this element to the parent element to which it's being applied. So it is going to be at the end of div. And yes, it's going to be after this maybe error, even if the error at that time was not rendered. This modifier is going to reserve the spot for the error. So again, everything is in the order in which it looks to be. You're calling amend after you've instantiated text input. This is already here. So this div is going to be at the end of this text input div. Let's look at rendering asynchronous or deferred values in Laminar. And actually, let's also compare it with React because the difference is pretty illustrative. First of all, apologies for using null, which is not something we normally do in Scala. I just wanted to make this slide easier to digest to a broader audience, hopefully including some JavaScript developers. This Laminar snippet renders an input element where the user will be typing their email address, and as they do so, we will be validating their input and rendering an error message right next to it if there is any. Now, we don't want this validation to happen in real time on every keystroke. We actually want the user to stop typing for 1 second before we show the error. Web developers will recognize this timing logic as the debounce function. And in Airstream, we have a debounce operator that works similarly but on streams. Specifically, it creates a new output stream which listens to the events on the input stream and emits its own event only after the input stream stops emitting for 1 second. Everything in this component should look familiar to you because we have covered it in previous slides. If you didn't want to delay the display of the error message, you can just remove the debounce operator and this will still work. And conversely, if you wanted to add delay logic to your Laminar component, you just use the debounce or throttle or delay operator depending on what you want, and you will have a working component with no other boilerplate, no more effort. And this is exactly my point. In Laminar, there's nothing special you need to do to work with asynchronous values because Laminar is designed from the ground up to work with observables, which are already asynchronous values. If you're familiar with React, you might be wondering, well, what happens if we unmount the component immediately after the user stops typing? In this case, the debounced Airstream will emit 1 second after that, so after the component has already been unmounted. Won't this cause a problem? Because, in React, you can't set state after the component is unmounted, you'll get a warning. Well, in Laminar, this is not a problem because the debounced event stream will not actually emit after the component has unmounted. Because as you remember, observables are lazy, so they will only emit if something is listening to them. Now, what's listening to this airstream? It's this observable on the right here, and it's used in this modifier which starts up the observable. It creates the subscription when the component is mounted, but it kills the subscription when the component is unmounted. So as soon as the component is unmounted, we stop listening to the airstream, and so it will stop emitting. It will not emit after the component is unmounted. And well, this is what automatic memory management and automatic lifecycle management is in Laminar, and it solves this kind of problem. Now let's see how much we need to suffer to implement the same logic in React. This is only pseudocode to save space. I'm sure anyone who used React will know how to write an actual component in this pattern. Well, let's see what's going on here. The render method looks a lot like what Laminar is doing, with the notable exception that the error variable we're now getting from state. And this is because in React, state is the only reactive variable that the component is allowed to manage. Unfortunately, React's state API is entirely callback driven, and that goes for both when reading and writing from state. So when we're reading from state in the render method, we can't apply any asynchronous transformation to it, such as debounce or delay. So instead, we have to apply the debounce transformation when writing to state, and that is annoyingly verbose and indirect. The reason I put the error update logic inside of the component did_update lifecycle hook is because in React, this is the only way to reliably run this logic in response to any update to the email field on state. And this is what we want. In reactive programming, we want the derived values to be automatically calculated, and we don't want to do the calculations manually or even to trigger the calculations manually, because all of that should be handled by updating the source value, so the email value in this case. And this is as close to this paradigm as we can get in React. Implementing this lifecycle hook is really annoying. First, we need to filter out the irrelevant callbacks that don't update the email field on state. Then, before trying to set state inside the bounce, we need to make sure that the component is still mounted. But React doesn't provide a way to do that out of the box, so we have to implement it ourselves using more lifecycle hooks. Finally, the debounce function is not actually provided by React, and the suitable debounce function is not provided by --, or underscore out of the box either, because this if condition needs to remain outside of the debounce, and you will find that you need even more boilerplate to make this work. And all of this is just to render a single asynchronous value React. This is basic stuff. This should not be so hard. Now, of course, you can use a third-party library to debounce your React state and 100 other third-party libraries to do other simple things that React isn't able to do out of the box. But that's not because React is just a small view layer and those are not its concerns. Rendering values, even a synchronous one, is a core concern of a UI library like React, of the view layer. But React doesn't include such functionality because its core model is just unsuitable for reactive programming. And it requires the collective effort of hundreds of developers who build all those third-party libraries to even be workable. All right, React rant over. Got this out of my system. Let's get back to Laminar. Modifiers in Laminar are so much more than just attribute value pairs. They're very diverse and very useful and very flexible and customizable. For example, this onMount focus modifier that we used to focus an element on mount, it's built into Laminar, but if it wasn't, you could trivially implement it yourself because it's just this one line, there's nothing else to it. It just uses a lifecycle hook in the most straightforward way possible. And say, what if, for example, in your application, you need to often react to the user pressing enter inside some of the input, specifically that button? Well, the browser does not expose such an event, but it does expose on key press, which fires on every key press. All we need is to just filter it to only include enter key presses, and then we can just save it into a variable as an event prop transformation. And now we can use it as if it was a built-in browser event, basically. Remember how we did onInput and mapped it to the current value of the text input node? Well, here we are doing the same, but with onEnterPress instead of onInput, as if it was a built-in browser event. But it's not. We've just made it here. The event prop transformation is actually pretty useful. It lets you use capture mode instead of bubble mode. It lets you stop propagation, prevent defaults, stuff like that, and also obviously filter and map the events to match what you want in the observer. Speaking of observers, when you perform these transformations like map, collect, filter, so far I showed you how to do it on the event side, on the left-hand side of the arrow, but you can do the same transformations on the observer side. Well, if it's a map, then it would be a contour map on the observer side. And so instead of creating a new event prop transformation, which is mapped, like here, it would create a new observer, which would now be not an observer of coordinates. This, what I've just selected, is an observer of a mouse event. And so you're doing the right thing by sending a mouse event to an observer of mouse event. Now, contour map is, well, like it feels inside out, and oftentimes it's out of place. However, in real life, you have boundaries between various components, and sometimes it's very useful to keep certain logic on one or the other side of this boundary to prevent unnecessary coupling. And this is where contour map becomes useful. You will feel the need for it when you're working in real life. Laminar is a small and unopinionated library. It might not have all the things you want from it because different people want different things from it, and we need to keep the core small. Just like in the text input component example from a few slides back, you don't want to bloat the core with everyone's opinions and everyone's needs because then it will be harder to use and harder to maintain. Instead, we want to create something very flexible, something that is easy to customize. And this is exactly the approach that we take in Laminar itself. For example, here is a display when modifier, which basically just hides or shows an element based on an observable of Boolean. It is trivial to implement. It's not built into Laminar, but it is trivial to implement. It is just one line, a straightforward line of code that you can have in your own project in under a minute. And you can have a whole library, a whole collection of these, some simple like these, other more complicated abstractions. And that library that you build up will be perfectly suited for you and your use case and your programming style. You can even publish it as like an add-on or something, but you will never have to compromise for someone else's opinion, someone else's usage patterns and needs or anything, right? You're going to just build it out for yourself. And this is the spirit of Laminar, is just do your own thing. We give you the tools and you do your own thing because it's easy and you'll get exactly what you need. Not some over-bloated library that supports everyone's use case poorly. You will get something that supports only your use case, but very well. Custom subscriptions is something I wanted to point out for extra clarity. Previously in our examples, on either side of the arrow, we used to have something Laminar specific, like a child.text or onClick.map. Those are Laminar constructs. They are not just plain observables or observers, they're special things. Just want to show you that the arrow actually works with generic observables and observers. This is very useful because it gives you automatic memory management. This subscription is going to be created when the div element is mounted and going to be destroyed when it's unmounted and then created again if it's mounted again and so on. So it's just very useful for all of your custom logic. One notable use case is when you say onClick.map or .filter or something. That is, you're working with event prop transformations, if you recall, and those are not event streams. They don't have the full palette of event streams operators. For example, they don't support throttling events, but we can do this by grabbing the event stream of input events from a particular element. We can always do this. And that will be a real stream, and then you can apply throttle operator on it or flatmap or anything else that you might need. And then you can just pipe it to observer using this observable to observer syntax. And remember, in context just provides you a reference to the input node that we're working on. Custom modifiers you can create without any effort. You just extend the mod trait or even just create an anonymous class like this and provide an implementation for a single method, which just accepts an element to which is being applied and simply does something to it. It doesn't need to return anything. It just needs to do something like set a property. And of course, you can use this as a first-class modifier in any element. Well, I mean, this modifier is specifically for input elements, so you can only use it for input elements, but you get the idea. It's a first-class variable, first-class modifier. Oh, and here's an Easter egg for you for suffering through all these slides with me. You know the colon equals method? It is a pain to type. It is a space, colon equals space. That's a lot of work. So wherever you see colon equals, you can also just use the apply method. The reason I use colon equals is because it's just easier to explain to people because other libraries use this. But personally, I always use apply in my own projects, and this is equivalent to CLS colon equals name input. Just a small hint. Before we talk about integrating Laminar with React and other libraries, let's review the main challenges of observables and how Airstream solved that. Event streams are great at representing streams of discrete events, such as user clicks, but in UI applications, we also have to work with state, not just streams. And state is different from event streams. It has, for example, has a current value at all times, and it's basically supposed to represent the value that changes over time, as opposed to discrete events coming in. Unfortunately, event streaming libraries typically encode state as a subclass of event stream, usually calling it something like memory stream, and it ends up being just an event stream with an initial value that remembers its last emitted event as current value, sort of. Unfortunately, this abstraction breaks down very easily. For example, if we take a stream of numbers and we create a state from it starting off with 0, and then we say filter that state to only include positive numbers. Well, that's a contradiction, right? State always needs to have a current value, but the initial value will not pass this filter. How's exactly then it's gonna work? It is a bit ridiculous seeing this all on one line, but in a real-life application, the part on the left could be in a whole other component and you wouldn't know what's there. And this condition might not be as obvious that it will filter out the initial value. Moreover, if you have a state as a subclass of event streams, you might not even know that the variable you are filtering is state, because its type might be event stream. And it could be state, right? But you don't know that it is. So you might be thinking you're filtering events when you are free to pass a memory stream or state kind of variables in there, and then it will break. Well, the problem is that you can't filter state safely in principle, but event streaming libraries let you do that because they treat the state as event stream, which it is not. Laminar has a special type for state called signal, which is not a subclass of event stream, but both of them are subtypes of observable, which has some shared functionality. But filter method is one of those methods that are specific to event stream. It's not defined on signal, so you can't actually filter signals in Airstream, which would prevent this problem. But of course, you still can achieve the same outcome. You just need to be slightly more explicit about how you want to handle this edge case. For example, if you don't want to filter the initial value and just want to filter subsequent values, you can use compose changes operator to filter just following events. And then it will be obvious to you that the initial value is not touched by this transformation. If you, on the other hand, want to throw an error or something when the initial value doesn't match the filter, well, you can arrange that as well in a different manner, but you will know what you're asking for and what you're getting. So essentially, you're trading a bit of explicitness for more safety, and I think that's a good trade-off in this case, and it helps a lot. It also, is very useful that Airstream has both state and the event stream reactive variables in one integrated system, that you can easily convert one from another and integrate like this, for example, because sometimes when people are fed up with representing a state using event streams, they end up representing state with another unrelated library and have to integrate that state with event streams from another library. and then just becomes a mess because it's not designed to work together. But Airstream is designed for event streams and state to work together. Glitches are a really annoying problem in observables and is what motivated me to create Airstream in the first place for the most part. Basically, a glitch is when a streaming library allows you to observe an inconsistent state that shouldn't exist. Let's look at a diamond case example, the simplest one. Say you have a stream of numbers and you derive a stream of booleans which indicate whether those numbers are positive or not, and then you combine them back into a single stream. And this is what usually happens when glitches usually happen, when you combine several observables into one, and one of those observables depends on the other. And so this output stream will emit a tuple of the input number and then a boolean indicating whether that number is positive or not. So imagine you emit number 1 and then number -1 into the input number stream. What you expect on the output would be a tuple 1 and true, and then another event with a tuple -1 and false, because 1 is positive and -1 is negative, not positive. And this is how Airstream behaves. However, in many libraries, including popular ones, you will actually get another glitch event in between those two, which will emit a tuple with -1 and true. But -1 is not positive, so it should never be seen next to true. That's why it's glitched. That's why it's undesirable, because you might have logic that assumes consistency, which will break on this event. That is not the only way in which this is problematic, by the way. Another issue is that the input of this graph had 2 events, but we've created a third event out of thin air for no reason. This means that, say, if you're counting events somewhere downstream, you will have an incorrect count. You would expect 2 changes, but now you have 3 changes. Or if you're performing any side effects based on those events, such as making network requests, now you will make 3 network requests instead of 2, and actually one of them will be with incorrect data, so it might not even be the right request to make. So glitches are really problematic, and I hate them, and that's why Airstream exists pretty much. Airstream uses directed acyclic graph approach, which lets us avoid glitches pretty much at all times, except when we have loops in the observable graph. And when we do, we have it very well documented. We have designated spots for sort of glitches to happen, which are event buses and vars, and let's say when flat mapping streams. And you should read the Airstream documentation about this for more details, but the long story short is it works really great. You basically never think about glitches, you basically never experience them, because everything works the way you'd expect, and even if on paper something in event bus is a glitch, it is 99% chance that it's going to work the way you'd expect to work. Okay, I lied. Glitches are not literally the worst part of observables. The worst part is having to manage memory manually in a garbage collected language, which is specifically designed so that you don't have to manage memory manually. This is just lame and unsafe and buggy. Observables, as you know, are lazy and they're not going to run unless they have observers. But to add an observer, you need to create a subscription, which is a leaky resource. You need to kill it in order to release memory. You're going to leak memory if you don't do this at the right time. Other libraries like Outwatch are able to manage the lifecycle of the subscriptions that they create behind the scenes automatically, and they even provide a way for you to make use of that automatic memory management for your custom subscriptions. However, under the hood, you're still using, say, Monix, a streaming library that requires you to manually kill subscriptions that you create. So you are free to bypass Outwatch or whatever other UI library you're using to create a subscription and then not kill it at the right time, and this will compile, and that makes me sad. In Airstream, I solved this problem by requiring that the user provides an owner when creating a subscription. And the owner is what's responsible for killing the subscription. So essentially, you can't create a subscription without at the same time saying when it will be killed. And you might think, well, hold on, isn't this just moving the problem to another layer of some weird owners and just having to do it manually with owners instead of manually do it with subscriptions. And yes, sort of on the streaming library level. However, when you're using Airstream from Laminar, you don't deal with owners because Laminar provides you those owners, just like Outwatch automatically manages memory of their subscriptions. We automatically manage memory of our subscriptions. For example, when we bind a stream to an observer, we use the owner of this div essentially. We create the subscription when the div is mounted, and then it remains active, and then we destroy the subscription when the div is unmounted. So all your subscriptions that relate to an element will just get automatically garbage collected when the element is removed from the DOM, which is 99% of the time what you want. For those 1% of the times, you can grab the owner of some node in Laminar manually. Again, this is not something that you need to do with any regularity. It's like super rare for like super custom logic. And that's what's great, because most of the time you just don't think about it. And when you do, we default you to please provide some clarification instead of just doing it the unsafe way. Similarly, how with state, we choose explicitness over unsafety. Laminar is a really small library. All it does basically is let you build a DOM tree using observables to respond to changes. And those are the things that you will actually spend the time learning. Observables and functional reactive programming, JavaScript DOM and the browser platform, and just Scala language features in general, the composition and abstraction techniques. This is the kind of knowledge that you will be building up when learning Laminar, and it is not specific to Laminar in any way. It will stay with you when you go on to work in other UI libraries or even on the backend. It is universally useful. And this is really the goal of Laminar, is to minimize the core by building on a bigger but still reasonably sized foundation, of this fundamental knowledge. Like, we're not going all the way into category theory or typed effects into anything like that. I think personally that this is too complicated for UI applications. But it is also not like React. React is a pretty big framework at this point, and it requires you to learn its way of doing everything, all the components and the virtual DOM and stuff like that. It's all very React specific. And I mean, even when it's not like strictly speaking React specific, it's virtual DOM specific. Those skills are not really transferable to other UI libraries or to working on the backend or just anything. And in fact, with React having such a big ecosystem of libraries, oftentimes what you're doing when you're learning with React is just Googling React how to do this, downloading some React left pad, whatever, and using that instead of learning how to do it in maybe one line of code more, but doing it in a native way in the JavaScript DOM. So I prefer not to download like 200 packages for every little thing and just to learn the way of doing things natively, because it is pretty easy at this point. And Laminar actually promotes this. We expose the .ref on every element, and then you can do whatever you need to it using native JavaScript methods. And you will find that those are not as scary and not as cumbersome as you might have thought for a lot of tasks. React is a fine library, all things considered. I've used it myself with good results, and it's clear why it's so popular. But I do have quite a few misgivings about it, mostly about the rigidity of the component pattern that it prescribes. You have to have props as input, state maybe internally, and finally a virtual DOM element as output. Regardless of what the functional or class components or higher order comments, whatever that is, all of that follows the same patterns, just with different syntax. And it's really hard to stray from this pattern in React because it's just not designed for it. Regular state, for example, can't even exist outside of components. And regular state together with virtual DOM is what drives declarativeness and reactivity in React. In Laminar, that's observables, and observables are general purpose. You can use them for all sorts of auxiliary logic, such as network requests. But in React, you can't really do this. You will have logic in different styles, some of it declarative inside of components and others in some other style that is not supported by React. Global state in React is a requirement if you want to have any state outside of a component, and that is achieved by libraries like Redux and Flex, which bring their own ideologies and completely different APIs into the equation, which is again has no reason to be different. In Laminar, all of that is just observables, whether global or local, with exactly the same API. And to pass information from child component to parent component, we still use callbacks in React as if it's 2005 or something. JavaScript ecosystem has moved on from callbacks to promises a long time ago, and yet we're stuck with callbacks in React. Promises, to be fair, they can't be used to represent event streams, right? You need actual event streams for that. And event streams are not as popular in JavaScript ecosystem yet. But, well, that's just another failing of it as far as I'm concerned. Speaking of promises, you can't even render a promise straightforwardly inside of a React component. You need to mess with the state to do that, to put its value into state as it resolves, or whatever hook alternative to that is they have nowadays. But basically, again, you have to channel everything through the React approved way of doing things, and that's just annoying. There are, of course, many libraries that help you with all of this for all kinds of tastes, but I don't want my UI foundation to be a collection of 100 disparate libraries and helpers. I also don't want a big monstrosity that is opinionated about how to do all that functionality. I want something that is small but very flexible, and that is what Laminar is intended to be. React.js, the original Facebook JavaScript library, was unsurprisingly designed to make use of JavaScript's dynamic typing and idioms. Dynamic typing doesn't mean there's no types in JavaScript. It just means that the types aren't statically checked. And React.js does work with types, but it works with structural types, which are found in TypeScript or Facebook Flow, whereas in Scala and Scala.js, we normally work with nominal types, which work differently. This kind of disconnect is a problem when you want to use React.js from Scala in a type-safe way. Well, it's not just that problem. There are several disconnects between JavaScript and Scala. And to solve these problems, we need a library like Scala.js React, which is an interface layer which wraps around React.js APIs and provides idiomatic and type-safe APIs in Scala around these. Scala.js React specifically is pretty opinionated, I would say, a library. It has its own APIs like callback and backend scope to make usage of React more functional in a Scala understanding of the word. Slinky, on the other hand, is another such interface library for React, which is more faithful to the original React API, but it does require some macros, and even though they're pretty straightforward, I personally don't really like invisible code. But it's still a good experience to use as Slinky. These interface layers solve the type safety issue, so they let us use React.js from Scala, but they can't really solve the underlying architectural problems of React that I've complained about before. For example, if you've worked with React.js, you know that function props could be a performance problem. When you pass a function as a callback to, say, the onClick prop to a child component, you need to be careful not to create a new function instance when you're doing this on every render call, because then all the props that you pass to the children will never be equal to the previous props that you pass to it, because the onClick instance would be new and not equal to the previous version of itself. And so React will think that you've updated the props for the child component, even though you didn't really. And it would re-render the child component every time it re-renders the parent component. And if you're not disciplined about this kind of thing, your entire application might be full of these inefficiencies and could be pretty slow. Because we're using React.js not directly from JavaScript, but indirectly from Scala through a translation layer, this indirectness has a bit of a cost, and so performance problems tend to be a bit exaggerated when using React from Scala as opposed to when using React natively. Not dramatically, but I would say noticeably in my case. And you can make mistakes that just kill performance for good. For example, you can have a top-level component, and if you put any state in there, and that component also renders your whole application, every time you update that state, you need to be very careful to not have function prop issues so that your application is not re-rendered whenever you update the state. I actually did run into that problem when typing in an input. It took half a second on each key press because React was re-rendering the whole application, and it wasn't really such a big application. So these kind of issues are obviously solvable. For example, the function props in Scala.js React are solved with reusability helpers, and in Slinky we use just standard React boilerplate for that kind of thing. But it is still boilerplate, and it's annoying to have to write it out for such a simple thing as passing a callback. On the next couple of slides, I'll show you how to render laminar elements inside of React components and the other way. To understand the problem better, let's consider the difference in approaches to propagation of state into the DOM between Virtual DOM and Observables. Virtual DOM doesn't really know anything about the data flow in your application. All it knows is how to render an entire component given the entirety of this component's props and state in React. That means that if you want to update just one prop, Virtual DOM doesn't know what to update on that component. It needs to first re-render the whole thing using the entirety of the props and state to do that. And it might even re-render some of its children and some of their children. Only then it will be able to figure out a new virtual UI state and diff it with the previous virtual UI state and produce a set of instructions to update the DOM and then execute those instructions. That is how it works, but the point is it doesn't know by looking at what's updated in the props. It doesn't know in advance which, I don't know, elements or attributes need to change in the DOM. It only deals with like components. This is the most granular level that it deals with. Observables, on the other hand, don't really have this concept of components or any like grand picture. Like you can't re-render a component on demand using observables like you can in React. But on the other hand, observables know precisely which parts of the DOM depend on which data, and they know which data depends on which other data. Because you literally define your data flow graph using observables in Laminar. So if you're sending an event into an event bus, or if you're updating a field inside a var, these updates will be propagated through the data flow graph to only the parts of the DOM or other listeners that depend on this particular data, or on this particular field or this particular event. And this is because observables are lazy. So when data comes, when an event, a change in state comes into that observable graph, it flows through it like through tunnels, through a set of tunnels, but it only goes into those tunnels where there's a destination, where something is actively listening for it. This is how we can update attribute values or DOM elements very directly in Laminar without the overhead of re-rendering the entire component. So let's see how we reconcile those approaches in practice. Let's say you have a Scala.js React application and you feel like trying out Laminar. There are a few ways you could approach this, but you could, for example, create a new page or screen in your application, which at the top will be Laminar, and then it will maybe use some of your existing React components. So well, let's see how to use React components from inside Laminar. Let's say you have a My React input component, which might be one of your own, or it might be coming from a third-party React library like Ant Design or Blueprint. This is how you can use it from Laminar. We basically wrap it into a Laminar element. We create a Laminar wrapper component that accepts a signal of whatever your React component accepts as props. So I assume there's some props class in there. Now then we just listen to the props update, and whenever they change, we call React DOM to render the React component at this location inside this div. Because it's virtual DOM, it will efficiently update the contents of this component on subsequent renders. It's not going to recreate it from scratch every time. If your props have any callbacks defined on them, such as, for example, on change or on input. In Laminar, you want an event stream of those events. So in the calling component, you will just define an event bus and provide the writer callback for that event bus as on change. And when the React input component calls on change, your event bus.events stream will emit whatever React passed as the parameter to the onChange callback. This is how you can translate both props down and callbacks up data flow directions. Finally, you need to tell React when your Laminar element is unmounted, and that is again very straightforward. We simply translate Laminar's lifecycle hook into React's unmount lifecycle hook. As you see, this is pretty easy. You don't even need a library for this translation. It's just a few lines of code. Let's look at the other direction now. Instead of migrating starting from the root node, let's see how to migrate starting from the leaf node. That means rendering a Laminar element inside a React component. For example, let's just take the same type signature that we used last time. So our Laminar element will be an input element accepting a signal of props and returning a Laminar element. And our wrapper React component will just accept props as props. And it will not have any state because the internals of this component are managed by Laminar now. We need to define a props var to store the updated props that we get from React. And we start off with props as they become available on the first mount when we mount a React component. Incidentally, at the same time, we render the Laminar element into this empty div that we've created in React. And this is just going to happen once. All the subsequent updates will be handled by the component did update lifecycle hook in React, which will simply update this props var with the next props. And as you see, the updated props will flow into my Laminar input component through the var's signal. Finally, again, when we unmount the React component, we need to notify Laminar about the need to unmount it so that it frees up the resources, cancels all the subscriptions and stuff. And this is how we do it, just a simple translation between lifecycle hooks of React and Laminar. Just a quick note, you might notice we're using a different import for Laminar here. We prefix all Laminar values and types with L just to disambiguate React values from Laminar values and types. You can also use it when just writing a regular Laminar application. You'll have L's everywhere, but all the implicits and everything that you need is still available from such an import. As you can see, using Laminar from React and React from Laminar is very easy. We just showed you how to do it right here without any sort of compatibility layers that you would need to create. This is a good way to gradually migrate from React to Laminar or just to try out Laminar in your application. I've been saying that Laminar is more flexible than React, and a good way to demonstrate that is to implement React's component pattern in Laminar. Well, this is a bad idea. Don't do this. This is just for demonstration purposes. If you want React's component pattern, just go and use React. It's exactly how it's designed. This is not a good fit. It's simply possible. So we define our props class, our state class, and we define a Laminar component that accepts a signal of props and returns a modifier for the parent element. I'll explain why a bit soon. We need a way to convert initial props into initial state, and you need to provide this method here. We also have a render method which has access to a signal of props and a state var, which means props are read-only, but state you can both read and write. This is how you could use both props and state, for example. You can combine them. Finally, what our component returns, as I said, is a modifier, right? And it's a modifier that when the parent Laminar element is mounted, it inserts this div that we render here, but not before initializing the props, the initial props and the initial state and creating a state var for it. So looks a lot like a React component. It has the kind of similar type signature on a high, like, philosophical level. But this is not virtual DOM. This is real Laminar component inside of it. There's no actual React in here. Anyway, it just looks like React. Once again, just probably not a good idea to implement your components this way, but it's definitely possible. You might be thinking, well, Laminar sounds great, but it doesn't have all the large collections of UI components that the React ecosystem has. Why don't I create wrappers for all those React components and use them from Laminar? And you can do that. As you saw, that's not very hard. However, there's a better fit. React Virtual DOM and Laminar Observables, as we saw, are very different approaches to the same problem, and so you're going to run into some friction working with both of them in the same application. But, as you know, web components are essentially custom elements with custom attributes and custom props, custom CSS props defined on them. And Laminar is great at managing elements and their attributes and props. This is what it excels at. So let's see how we can use web components from Laminar. We have created an example interface to a Material UI button component. I will show you that on the next slide, but here let's just see how we use that interface to create a button element, a Material UI button element. So we can set attributes defined on the web component. We can even set them to read from a signal or stream, like in regular Laminar. We can set custom props, CSS props. We can listen to generic JavaScript events or to events that are specific to this web component that are defined in it. We can insert Laminar elements into slots of the web component, and those elements can even be reactive. They can also listen to observables, and this will work just fine. And we can use lifecycle hooks in Laminar to run some logic, including, for example, calling methods defined on the web component element, because again, in Laminar, you have access to the underlying element. This method doesn't exist on the actual Material UI element. It's just like to demonstrate. If there was something there, we could call it. So let's look at what the interface looks like to make this possible. Here's the implementation of this interface to the Material UI button component. It is pretty straightforward. Let's just go through it top to bottom. First, we need to import the JavaScript dependency and actually evaluate it so that it's not dead code eliminated. This will register a custom element on the DOM called the MWC-button, and we will make use of it in Laminar. Raw element is just the type that your component exposes for the element itself. Your web component might define some methods or some values on its element, and this is where you can define those methods, and you'll be able to call them this way. DoThing is not a real method because the button doesn't actually happen to have any methods defined on it. It's just defined for demonstration. So the first thing we do is we create a custom tag for this button, which is basically how we create all the other tags, like div or span, but we create it with the name of the component's custom element here. This is a Laminar tag. This is how Laminar does this under the hood. Next, we just define props and attributes and styles too, again, in the same way Laminar does this under the hood. You don't need to define anything that is standard. For example, ID here actually is aliased to the ID attribute already defined in Laminar. It doesn't have to be here. This is just for demonstration. You can use any attributes and props and events already defined in Laminar with custom elements, with web components. So there's not much else here. Oh, well, slots, web components have slots in them, and the way they work is basically you have to pass an element as a child to this custom element and simply provide a slot attribute to be equal to something that the component understands, some special value. In this case, that's an icon, so that's how we can set an icon for this button. And finally, the apply method with a bit of a complicated type signature that allows us to do this underscore, that ID, or that label syntax. This is just my personal preference. You don't have to do it the same way. Ultimately, all you need is to call the tag with an argument list of modifiers for that tag in exactly the same way as you would create a div or a span element and pass the modifiers to it. Everything else is just opinion. As you see, web components are pretty easy to define an interface for them. It is not much more involved than, say, just defining an interface to a native JavaScript trait or class. You just use slightly different syntax to define the attributes and the props available to it so that you can work with them individually in exactly the same way as in Laminar you can work with individual props and keys. So this is a great fit for Laminar's model, and this opens up a great opportunity to use high-quality Material UI or any other web components that people have implemented, because, well, those web components have been designed to be usable from any library that is good at manipulating elements and attributes, and that includes both Laminar and React. So go ahead and build your Laminar application using web components, or write your own. Either way, it's going to be great. This is the end. You've reached the end of this long video. Congratulations, and thank you for watching and listening. I've been recording this for several days and I literally can't talk anymore, so you will have to read from now on. Thankfully, we do have extensive and current documentation for both Laminar and the Airstream. We have a bunch of examples and some add-ons such as a Waypoint, a URL router for Laminar. So check all that out. Join us in Gitter. We're a friendly bunch. If you are already enjoying Laminar, I have just opened up sponsorships of the project on GitHub, so please consider that. In fact, shout out to Yuri and Dufin, who have already signed up as sponsors even before I had the chance to announce it. So thank you for supporting me, and thank you for watching.